All right, so we're going to finish up by looking at 4.2 Part 2. And yesterday, we looked at graphing problems where the degree in the top was less than or equal to the degree in the bottom. When you do that, you always get a horizontal asymptote. You either get a horizontal asymptote at 0 if the degree in the bottom is bigger, or you get a horizontal asymptote at the quotient of the coefficients if the degrees are equal. Well, when the degree in the top is greater than the bottom, the horizontal asymptote goes away. You cannot have a horizontal asymptote when the degree in the top is bigger than the bottom. That's going to be replaced with another kind of asymptote, and the kind of asymptote depends on the problem. What it really depends on is how far apart the degrees are. The further apart they are, the more complicated it gets. And by how far apart, I mean, like in this problem, that's a degree 3, that's a degree 1, that's a difference of 2. Okay? When there's a difference of 2, you're going to get a quadratic asymptote. If there was a difference of, let's say that was a 4 and that was a 1, the difference now would be a 3. That would be a cubic asymptote. So the further apart these two exponents get, the more complicated the asymptote gets. We don't look at any beyond having it be 2. 2 is the highest. Okay, so any question on the difference between what we did yesterday and then what we're going to do today? All right. So what we're going to look at today is something a little bit different. We're going to call it the EBA, the end behavior, asymptote. And this is what takes the place of having a horizontal. So I guess yesterday you could say we looked at end behavior asymptotes, but the end behavior asymptote was always horizontal. Today the end behavior asymptote might not be. And I'm going to show you how you find the EBA. Okay. When you divide these two things, right? Like if you had a polynomial in the top and a polynomial in the bottom, maybe something like that one. When you divide them, you're going to get a quotient and you're going to get a remainder. The quotient is the EBA. So it's not a new calculation you haven't done before. It's something we've already done. The quotient is the EBA. So there's a couple ways you can find an EBA. You can do synthetic division, or you can do long division. And when you get the quotient, that's the EBA. Now, how come the remainder doesn't matter? Well, let's think about it. It's basically what I just wrote that. This is the way I've written long division problems a lot. Quotient plus remainder over the original denominator. Think about what's going to happen to this as x gets bigger and bigger and bigger. Right? If you have a remainder, like in this case, when you divide this out, you're going to get a remainder that's a number. I don't know what the number is. We're gonna do it. But let's say the remainder was 5. What's the original denominator in that problem?
X minus 2.
It's x minus 2. So let's say the remainder comes out to 5, and the original denominator is x minus 2. As x approaches infinity, what happens to this fraction? 5 over x minus 2. Yeah, it gets closer to 0, and basically this part has no effect on the problem at all. Maybe for small values it would, but as x starts to get really, really, really big, this part gets really, 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 really small, and it approaches 0. So the only thing that's left that's significant is the quotient, and that's called the EBA. So let's try this. Let's find the EBA. Is this a problem I can use synthetic, or do I have to do long division? I can use synthetic, yeah. I'd rather use that if I can. It's faster. So, does everybody have the left page so I can make the right page bigger? Yeah.
Can you just really quickly go over how the analogy can use it?
It depends if the denominator is x minus a number or x plus a number. As long as it fits that pattern, you can use synthetic.
So if it was x minus, that means you can do, that means like you put the 2 in the box.
We're going to put the 2 in the box.
Okay.
But if it was x plus 2, that would basically be, well,
You'd use -2, right?
Yeah. You can actually use synthetic division when the denominator is a little more complicated than that, but I never taught you how. I'm not familiar with how to do it, but you can.
if it's two numbers, you just find what the 0 of it would be. Like for x minus 2 is positive 2, for x plus 2 is negative 2.
Yeah. Yep. Whatever. Yeah. Or whatever is right there. Yeah. Okay. Write your coefficients. Don't forget your 0 for the x term. There is no x term. All right. Bring down the 2. We got 4, 0, 0, 0, 2. Wait, is that what I guessed the remainder was?
Wait a minute. Why did you say 2?
Subconsciously, I must have remembered that from when I taught.
Wait, why did you say 2 with 0?
Why did I say 2? Why did I do something wrong?
2?
Yeah, you
Oh, 2, bring down 2 times 2 is 4. And then add that, you get 0. 2 times 0 is 0.
Which equals 0.
0. 2 times 0 is... Oh, I just wanted it to be 5, that's all.
It's 3.
I wanted it.
Remainder 3.
All right. So now, what's my... let's start with the quotient. What's my quotient in this case?
2x squared minus 4x plus 0.
So your quotient,
The question is
Right
just
there.
2x squared.
just 2x squared.
Oh,
We have nothing else.
What's your remainder?
the remainder is 3
Remainder is 3.
over x minus 2.
Well, the remainder itself is just 3. Just 3.
When would you do it divided by the denominator?
If you were writing the answer to this entire problem, I'm kind of breaking it down separate.
So just for synthetic division, that's the quotient and remainder.
Yeah. And what's your EDA here? Yep. 2x squared. It's the same thing as the quotient. So it's kind of redundant to ask for both. But if you know that they're the same thing, it really isn't any more work. And remember, I already answered this. What happens to the remainder as x gets bigger and bigger? Well, if you write it as quotient plus remainder over denominator, I'm really asking what's happening to that. And what happens to it as x gets bigger? It approaches 0. Yeah. So what happens to the remainder, I should say remainder over denominator part? That's a little more accurate. It approaches 0. So we're going to graph this one. Now that we did all the work to find the EDA, I'm going to show you how to sketch it. Yeah.
I know this one isn't, but if it was like a full quadratic, like there were all 3 terms, would that still be the EDA, or just the first one?
No, the EDA is the entire quotient. It's that entire box. In this case, it just happened to be zeros. So, a couple terms that we've mentioned just to make sure we're clear on what they are. Right? There's a difference between the EBM and the EDA. The EBM, that's the easy one to find. It's just the highest degree term in the top divided by the highest degree term in the bottom. The EBA, you need to use long division. Sometimes the EBM and the EDA are the same. They can be. Sometimes they're different. We don't really talk about the EBA with the kind of problems we did yesterday. With the kind of problems we're doing today, we can talk about both the EBM and the EBA. Now, if the degree of the numerator is less than or equal to the degree of the denominator, that's the kind of problems we did yesterday. What kind of asymptotes did we always get yesterday?
opposite? Like, it would be one quadrant and the other one would be the other quadrant.
So what about the asymptote itself? What kind of asymptote was it? We had horizontal. Yeah. What else?
Vertical.
And vertical. Those are both examples of what shapes? Lines. Those are linear asymptotes, right? Horizontal and vertical lines. But if that's not true, if the degree in the numerator is bigger than the denominator, then the asymptotes can start to either be slanted. That's like a one step up. And then up from there, they start curving. So we start getting quadratics first, and then it goes to cubics and more. The particular one we're going to graph, it has a quadratic asymptote. Any questions on that? Yes?
So the degree in the numerator is less than the degree of the denominator. We know what 1 over x looks like on the graph. Is that related to this? Because technically x is a bigger degree than just 1.
Right, that has straight line asymptotes, one horizontal and one vertical.
So do we know at what point it can start to be curved? Or?
When the degree in the numerator is bigger than the denominator by 2. That'd be the minimum.
So like x to the 5th over x to the 3rd?
Yes, that would have a quadratic asymptote. Yep. So the degree has to be a difference of 2 at a minimum to start making it curve. A difference of 1 isn't going to curve, but it's not going to be horizontal. It's going to be slanted. You'll see. All right, so let's verify that this is the EBA. And the way we'll do it, I'm going to graph the original problem, and then I'm going to graph the EBA. And if I zoom out enough, it should look like it's getting closer and closer.
I think there was a problem with that in the homework yesterday.
Where the degree in the top was bigger?
Yeah, and it was only a difference of 1. Because, like, when you graphed it out, it, like, instead of coming up from the bottom and almost, like, going horizontally to the left, it, like, went back down to, like, a 45-degree angle.
Okay, I need to double check that. Because, yeah, we shouldn't have done one yesterday where the degree in the top was bigger.
I could have possibly typed it in wrong.
Wasn't that true? But 2.
Yeah. No, I could have been one of the questions I gave you too. I'll double check. Okay. Because we're going to be drawing things that are going to start to get very close together, I want the line to be as thin as possible. So I'm going to make it thinner just so it's easier to see. And the EBA came out to 2x squared. Sorry. All right, so EBA is 2x squared. I also want to make that one thin just because they're going to be coming together. And it's easier to see it if it's a little bit thinner. Okay, so you don't have to make it thinner. It's just easier for me to show you. Hit graph. Okay, so there's your original. And the one in red is going to be the asymptote. Now you can make that bigger. So you can see kind of at least on the left side. See how the blue and the red are getting closer and closer? It's because the red is an asymptote and the blue is curving towards it. Now, it should be something on the right side too. We can't see it. So where do you think I have to look to see what's happening on the right side? Yeah.
You need to look more up.
Yeah, I gotta look higher. So let's put the Y max on. Let's try 40. See how that looks. It's gonna make this curve in the middle look a little bit more squished because I zoomed out so much. There's the other part. So the graph basically is a parabola, but it's been kind of broken in the middle, and each one piece was bent up and the other piece was bent down. That's kind of like what happened. Right, so let's look at that one a little bigger. So on the ends, right, the blue part, it's getting closer and closer to the red. And then in the middle, there's something happening there. What kind of asymptote do you think I have in the middle of it?
Vertical.
Yeah, there's a vertical. So remember, a vertical can't be crossed. So what happens is it's almost like you just cut the parabola at that point and then stretched it and bent one side up and bent the other side down. And that's a pretty typical kind of graph for a quadratic asymptote. Right? And that's what I'm going to show you how to sketch. Right? It really isn't that much different than sketching what we did yesterday. It really involves just plotting some points.
Vertical and horizontal asymptotes can be like slanted if like the degree is different by 2.
Well, no. Vertical is always vertical. Horizontal is always horizontal. Horizontal can be replaced with a slanted one.
Okay.
But it can't. It doesn't. It's not like the horizontal. Yeah, it's just the horizontal is just gone. Right? If you have a slanted one, the horizontal disappears completely. But vertical always stays up and down. All right. So example 6. That's really just a sketch. And now we're going to try to do a sketch ourselves. Well, first thing you'd want to find here is the EBA, which we already did. What was the EBA?
X squared. Oh,
2x squared.
2x squared. Sketch that. Okay, that's a parabola. If you need to make a table, you can make a table. Pick some values to sketch your parabola. We could go 0, 1 would fit on the graph, 2 would be okay, and then I think 3 is about as high as I can go before I'm off the graph. Okay. When you plug in 0 for x, what do you get?
0.
Okay. So we're going to go right through 0, 0. How about when you plug in 1? 2? When you plug in 2?
4.
8. When you plug in 3?
18.
Okay. And it's going to be symmetrical because there's no shifts in the parabola. It's going to be symmetrical over the y-axis. So -1, -2, and -3 are going to give you those same values. Right. So you got 1, 2, -1, 2, 2, 8, -2, 8, 3, 18, -3, 18. 1, 2, 3, 1, 2, 3. And do the best you can to just try to sketch that. Right? I'll make it dotted after so you know it's an asymptote. Okay, so I'm gonna kind of come down and go like that. Okay, let's make it thinner and dotted. Okay. So what that means is as we start heading further and further left and right, our graph has to get closer and closer and closer to that dotted line. Not necessarily near the origin. Only as you head left and right. All right. Vertical asymptote. What value would make the denominator 0?
2.
2. So let's put in a vertical asymptote. Just going to draw by hand at 2. Now remember, I had to go all the way to 40, or maybe I was at 50. I don't remember, to really see what was going on. You're going to see a little bit because I went up to 20. Probably should have even gone up to like 30. Oh well. Now I'm just going to plot some points. So go to your table. Let's start with some points near the vertical asymptote. What's a value a little smaller than 2? Yeah, 1.999. Okay, so you're going to be, right, just ignore, we don't need that right now. We're going to be at -3,000. So just before 2, you're going to be way down on your graph. Let me zoom out. So it's going to be way down there. And what's a value that's a little bigger than 2?
2.001.
Okay, let's check that out. So we're up at 30,000. So like way up there. Let me do these in a different color so I remember where they are. That one and that one. And now I need to check out what's happening left and right. I would probably check like the positive 1. That would be a good value to check. 1, -1. So 1. Remember my y-axis is scaled by 2s. That's why I only went down half a block. So 1, -1. I would check, you could check 0. So 0, -1.5. So 0, a bit lower. And now, as I start heading further and further to the left, these points have to start curving very close. So what would be another good one I could check?
-1.
Yeah, we could check -1. You can check as many as you feel you need to. -1, 1. Right about there. And let's try -3. I don't think it'll go off the graph. Barely. 17.4. So -3. 17.4. I'm just going to estimate right about there. Okay, so what's happening on the left side is it's going to look something like this.
Like half a parabola.
Yep, it's going to stay very close, start moving away a little bit, and then it goes through those dots, and then it comes down just like that. So that's that side. Now, the other part, this we just have to kind of get used to, is usually sandwiched right in that area there. So you need to try an x value in there. What would be an x value that I could try?
2.5.
Let's make that bigger so you can see it. Yeah, you could try 2.5. You might try like 2.1, 2.5, 2.9, because you're not going to be able to like go too much bigger than 3. You're going to go off the graph. All right. So 2.5, just barely. We're at 18.5. So 2.5, right about there. If we try like 2.2, well, we can see that it's curving up. So I can't really do much. I can't really do much more with that. So what's going to happen is it's going to be right in there. It's going to hit that point, and it's going to keep going. And the sides of it are going to look like a parabola, and the middle is broken. That's the most complicated one that we look at. There's a lot going on there, though. Yeah.
So could you, like, when you graph it, just like local minimum right there?
Yeah, there is a local minimum. I might not have done a great job finding it, but yeah, you could do that. Yeah. That'd be a good idea, actually. There's actually 2 local minimums. There's one down here.
Yeah.
There's a local minimum, there's a local maximum, and another local minimum. I think you could see the min and the max better when I was zoomed in.
Yeah.
But yeah. Okay, and because I only set my graph to 20, you're looking at like this when I did it. You're just barely starting to see like that other piece. So maybe I should have gone to 30 or 40. That's okay. Okay. Any questions on that? Okay. So keep in mind how to find your EVA, how to find your vertical, and then once you graph both of them, just plot points. Use the calculator to help you get as many points as you need. But I'd say 7 or 8 is probably a good amount. Okay, let's look at this one. All right. What's the degree in the top here?
3rd degree.
3rd, yeah. And the degree in the bottom?
2nd degree.
2nd degree. That's a difference of how much?
1.
It's only a difference of 1. So the top is still bigger, so you're not going to get a horizontal. But you're also not going to get a quadratic because it's not a difference of 2. A degree 1 is like y equals mx plus b. It's a step up from a horizontal line. It's a slanted line. And when we find the asymptote in this problem, it's going to be called a slant asymptote. Okay. How do I find the EBA? What do I have to do? Yeah.
Well, for this one, the EVA would be 2x, but to find it, you divide the 2x cubed by x squared.
Okay. Anyone have thoughts on what was just said? Yeah.
Did you have to do long division to find it?
Right. You have to do long division to find it. What you had mentioned earlier, that's the EBM.
Oh.
This is the EBA. So the EBA, you've got to do the long division. You can't do synthetic. It might look like it's going to be bad, but it's not, because it's only a 1 degree difference. So you're only going to have to do 1 round of long division, and you're done. Okay. So let's do x squared. And put in zeros for anything you're missing. We're missing what term?
On X.
So we're going to do a 0x minus 4. Okay, so the first step in the long division is what we said earlier. You do divide 2x cubed by x squared. And what does that give you?
2X.
Yeah, 2x. Multiply it back out. 2x cubed. And then what's
4X squared.
4x squared
6X.
minus 6x. And what do we do with the columns? We subtract them. 2x cubed minus 2x cubed is gone. What's 7x squared minus 4x squared?
11x squared.
It's not a plus, it's a minus.
3X.
Oh, yeah.
So it's going to be a 3x squared. 0 minus minus 6
Plus
6x.
plus 6. This stuff doesn't even matter because this is all remainder stuff. We're not interested in remainder, but if you want to do it, you can. And then,
3.
so
Plus 3.
we got that, we got that. And then what do I do?
Plus 3 in the top.
Bring what? Bring down the 4. That would be your next step. But now we're going to be done. What's x squared divided into 3x squared? 3. That's your EBA. If you want to keep going and get the remainder, you can, but we don't need to. That's why I said it's really just 1 full round of long division, and you're done. So the EBA is 2x plus 3. Right, let's graph that. What's the y-intercept? 3. And your slope?
2.
2. So graph your line. If you want to go the other way, you can. I'm just doing enough dots so I don't even have to use the line tool. I can just connect them pretty decently. So there's my EDA. What else did they ask for? Vertical asymptotes.
So you would just set the f of x equals to you would like factor out the bottom, the denominator.
Yeah, factor the bottom. And how does the bottom factor in this case? Yeah.
We would have x minus 1 and x plus 3.
Yeah, looks good to me. So your 2 vertical asymptotes.
Or plus 1 and negative 3.
Yep. Kind of annoying that it has 2, because that means it's going to break my graph into 3 pieces. If it only had 1 vertical asymptote, then my graph would have been broken into 2 pieces. Okay, so I got to deal with 3 pieces. So x equals 1. Right there. And then x equals negative 3.
Wait, where did you get the vertical asymptote again?
The vertical asymptotes are the zeros of the denominator.
Okay.
So we factor.
Oh.
Right, now you're going to end up with 3 pieces. A left piece, a middle piece, and a right piece. And
Don't we also have a horizontal asymptote?
no, the horizontal asymptote is replaced by the slant. Yeah. The only time you can get a horizontal is if these numbers are equal or the one in the bottom is bigger. When the one in the top is bigger, no, can't have that happen. All right, now we just got to plot some points. So we've got 2x cubed plus 7x squared minus 4, and divide by x squared plus 2x minus 3. Okay, what would be a good value I could check that's a little smaller than -3? Yeah.
-3.001.
Perfect. So when you're to the left, you're going to be way up high. Way up there. What about a value that's just a little bit bigger than -3?
Negative 2.999.
Yeah, -2.999. You're at -1200, so way down.
Let's go.
Thank you.
Now let's check 1.
Let's go.
Let's see. What's a value that's a little bit smaller than 1?
0.9.
0.9? You can go a little closer, 0.99. You're at -1200. What's a value a little bit bigger than 1? Yeah.
I'm not raising my hand for that as a question now.
No, what's bigger than 1?
1.001.
There you go. Yeah, what's up?
Is this like the same exact thing, just instead of doing synthetic division, you did long division?
We did long division.
Okay.
Yeah. All right. So 1.001, 12,000. So way, way up.
Let's go.
Bless you.
Wait, were the answers the exact same as what the other ones were?
No, a little different. Yeah, a little different.
Alright.
Okay, let's pick some x values in that area. We got to see what's happening on the left side. So what would be a good x to pick?
-4.
Yeah, -4. That's going to be perfect. We can definitely do that one. -1, 2, 3, 4. 1, 2, 3, 4. Looks good. And maybe one more.
-10.
Yeah, we could do -10. I can't do that one. I'm off the graph. We could probably do like -7. Yeah, we could deal with that. So -7, -10.8. So 1, 2, 3, 4, 5, 6, 7. -10.8, just barely off the graph. All right. So what's going to happen here? This is going to stay really close. Then all of a sudden, start to curve and get really close to that one. All right, so there's that one. Now, in the middle, it's a little different. We have 2 dots both on the inside at the bottom. Usually we have like one up high and one down low. We don't have that. Okay, they're both low. So I need to figure out a little bit more of what's happening in that area. What would be a good x value to check that?
-1.
Yep, we could do -1, -1/4. Okay, so right about there. How about another x value?
-0.25, like -1.25.
-1.25. Yeah, you can do that one. So you're negative, a little above -1. So -1.25, a little above -1. So maybe right about there.
-2.
Yeah, 0 would probably get a nice answer for that one. 1 1/3. So about right there. Well, that's enough. I mean, you can kind of see what we got to do. We got to stay close to this, and we got to stay close to that, and we got to go through those dots up there. So we go up, and we start to curve, and we come down. Okay, so there's the middle. Now we need to check the right side, and just like with the quadratic, you're usually sandwiched in that little space right there. So what would be a good x value to check there? 1.1. Yep, we could do 1.5. That's at 8. So 1.5, 1, 2, 3, 4, 5, 6, 7. Was it exactly 8? Well, 8.2. Close enough. And I mean, really, that's good enough. Because you're going to be stuck in that V shape. So
3. We should at least 3 points, right?
well, you could try to do a third one. The problem we're going to get into is if you try like 3, I'm up at, well, that one still fits. But if you do 4, you're off the graph. So 3 was about 9.4. 1, 2, 3. Yeah, so mine looks okay. Yeah, so that's what your graph looks like. I think the calculator is going to do an okay job trying to sketch that. Let me do zoom 6. So there's your left piece. There's the middle. Yep. And there's the little top part at the top. Okay, so how many asymptotes did we have there? 3. 2 vertical and 1 slant. As far as sketching something by hand, I would expect a slant to be the most common thing I would have you do. Question on that one? All right. What else do I have? Well, I don't want to go through the whole thing because this is similar to the last one. Just tell me what kind of EDA you're going to have. Is it going to be a quadratic or like a slant?
Slant.
That's going to be a slant. And how many vertical asymptotes in this one?
2.
1.
How many values would make the denominator 0?
Just negative
Just
J.
1. So you're going to end up with a slant and a vertical.
That's what I meant. Like two lines. That's what I thought the vertical asymptotes were.
So you could end up with something like that and then something like that. I think that's roughly what this one's going to look like.
So it's not I over X because it's like 1 degree more. So like that is it is it similar to I over X, like that one where like each point like gets really close to 0 but doesn't.
Like with imaginaries?
No. Just 1 over X.
Oh.
So like how is this?
Kind of. Yeah, it's kind of. It has these 2 kind of branches to it, like a hyperbola would have.
Yeah.
I don't technically know if that graph is called a hyperbola, but it is similar to the graph of 1 over X,
Okay.
except there's no horizontal.
The reason why it's slanted is because the difference in the degrees from the denominator and numerator is 2, right?
The difference here is a 1.
Is 1.
Yeah.
But it can still be slanted.
Yeah, as long as there's a difference of 1, then it will always be slanted.
Oh.
So if the top was an 8 and the bottom was a 7, that's a slant. Probably be a lot of other things going on too.
Yes.
But yeah. All right, let's just try to graph this one on the calculator only, not by hand, and find a complete graph. So we've done a lot of complete graphs. That's nothing new, but chances are there's something happening here that we're probably going to need to be careful about. All right, so let's put it in and see what happens. 7x cubed is x squared plus 2x divided by. You do want to put your parentheses around the numerator and denominator. Okay, so a little bit more complicated than I would have you graph by hand, which is why I'm not having you graph it by hand. What kind of asymptote would you expect there to be in this one? A horizontal, slant, or quadratic? Yep, there should be a slant. All right, let's do zoom 6. All right, so when I look at that, I'm not quite seeing the slant yet. 'Cause if I try to draw in a slant, it would probably be something like that. So my guess is the top piece at some point is going to start to curve, kind of back down like this. Maybe it's going to curve and start getting closer and closer to the green. Let's zoom up a little bit higher and see if that's what happens. Okay, so set the Y max at like 25 and maybe the X max at 15. Let's see if we can start to see the slant. On the bottom piece, I think I see it. There we go. I don't know if you can see, but it is starting to curve back a little bit. So now if I try to put my slant in there, it's probably something kind of like that, and it's going to keep curving a little bit closer. Okay, so I can see the slant, and maybe you want to see the bottom piece a little more. You could set your Y min lower. Now my question is going to be, there's still something here I'm not sure about. Okay, there's the two pieces. And that's a decent window for kind of seeing like the big picture of it. But what do you think I might want to check out a little closer? Oops. Something there I might want to check out a little bit.
The area where like goes along the x-axis.
Yeah, to me it looks completely flat for a long time. Well, we should check that out and see what's happening. So that's a good window. Whatever I've got right here, that's a good window for the big picture. But in order to really get a complete graph of this one, I think you need two windows. You need to zoom out, and we got to zoom in. So let's start by zooming in. Let's try right here. So what does it look like my Y min and max is?
0. Or not 0, but 1.
Yeah, I zoomed in from -1 to 1. And what's my X min there?
-3.
-3.
And then +1.
And my X max is +1. So let's graph that. What I'm going to do is just move that off the screen because we don't need that. And I'm going to put this picture zoomed in right here. Okay, so now we got that. Is anybody starting to kind of notice anything about that?
That's dip under the axis.
It does look like it actually dips under. So what we should probably do is zoom in even more. Right? I don't think I need to do anything with my X, but what I want to do now is just kind of zoom in on that part. So what do you think my Y min and max would be there?
0.2 would be safe.
0.25.
Yeah, we could do like 0.2 or 0.1. I think that's going to be enough to kind of see what's going on here. So let's do -0.1 and 0.1. And then we'll put that picture right here. Okay. So now we're starting to see what's going on here. If I asked you how many times this graph crosses the x-axis, and you look at the original, I don't know how you'd really give a good answer on that. You can't tell. It's too flat. It's too close. Even that one, it's kind of hard to see. But this last one, I would say you need to write down this window in order to have a complete picture of what this graph looks like. You can't see that from the big graph. How many times does it definitely cross now that we can see it? Yeah, it crosses 4 times. So I would say the answer to the question, you need 2 windows. This is a good zoomed in window. And whatever I had for the zoomed out, Yeah, I think we had like negative 25 to 30 or 40, whatever it was.
Did the thickness of the line have affected the picture?
The only thing that a thick line would do is it might make it harder to see, because if this line started to get really thick, especially in that area, it's like if I draw a really thick line, I was going to try to. So if you make the line really thick, then it's hard to see. I can't tell, is this once, twice, what's going on there? The thinner you make it, the easier it's going to be to see. Okay, any questions on that? All right, so just making sure that you zoom out or zoom in to check out everything that's really happening in a graph. All right, so that's the homework for tonight. I think it's 12, maybe 12 or 13 questions. So it's 38 to 42, 45 to 47, and 51, 52, 55, 62, 63. I will pause the video and I'll put a list of test topics that you'll need to know for tomorrow, and I'll put that online while you're at lunch.
Will the